I'm not even certain who's the first speaker of today. Stéphane is? So all the talks, as far as I know, are going to be in English. And so if you prefer French, I would suggest getting a headset. Stéphane, of course, could speak in... Are you in English, Stéphane? Yes. You are very kind. Your English is better than my French. So thank you so much for being here. We have after this 3 talks, don't leave. AGU would like to have a photo of all of us, a group photo. And ideally, we would go outside on the steps on the west side of the building, because it's a lovely area over there, but it's so hot and so muggy. Blech. Yeah? So I think what we'll do is stay in here. It's cool, and the temperature will be fine. And we'll take the group photo right after the last talk, so don't go away. And we'll take it in here. I don't know which will be better, either to take the picture with us standing in the middle and the photographer here, or us standing here with maybe Chapman's slide in the background, and maybe the photographer can stand up on the balcony. So we'll try. I'm leaning more toward us being here. It'll be a little cumbersome, but we'll all fit, and it'll be a lovely picture that would be really nice. AGU would very much like to have that. I think that's my only announcement. Shall we get started? Jose, would you like to start us off and introduce the first speaker? Stéphane?
Good morning, everybody. I think we have today the session of Cuvette Centrale. We have 3 presenters. The first is Mr. Stéphane. After 3 presenters, we have some questions after each presentation, and then we'll have we'll have a session of poster, and after session of poster, we have a discussion for the session. We'll try to solve the hypothesis of given to us for the session. Now I'll invite Mr. Stéphane to do his presentation. You have the floor, Mr. Stéphane.
Thank you. Tu crois que je suis... Do you think I am fired? Is it working? Yes? So good. Yes? Good morning, everybody. So I will try to make this presentation in English, and I apologize for all those who don't understand if it's either English or French. And so this presentation will be a bit broader than just the Cuvette Centrale, because it's, I will try to convince those who don't trust in satellite data that they may be of use, okay, together with the in-situ measurements, of course, but there is quite a lot of information that can be gained from the satellites. So I make this presentation on behalf of Melanie Baker, who is the first co-host here. Oh. Well, whatever. So Melanie, who apologized, but who couldn't make it. But I highlighted the name of Adrien Paris within all my co-authors, because he was a very great help for preparing this presentation. So yesterday, we could see that most of us were complaining because of the lack of in-situ measurements that limits all the studies that everyone would love to do in the Congo Basin. But I do think that we have to understand that it will not come back. The era of plenty of in-situ measurements will not come back because it's critical in the Congo Basin for sure. But actually, it's global, okay? It's not only in the Congo Basin that the amount of in-situ measurements available is decreasing dramatically, okay? So, for sure, we have to deal with that. And then, what do we have if we have no in-situ measurements available? We have the satellite data, okay? And then, the best position that we can have is to see, okay, what is the information in the satellite data? What can we do with this data? Either in the parameters that they can measure straight. I mentioned the water level, the precipitation, the mass variations, the inundated surfaces, or the volumes, the volumes of water stored either on the surface or in the ground, or using models that can ingest these satellite data for quantities that are not observed straight, such as the discharge, the evapotranspiration, and so on. An important point also that was discussed yesterday is that most of the satellite data are distributed for free, okay, and are available to anybody who wants to use them. And for sure, all those that I present today are distributed for free. Some are sold, but not in all those that I am presenting today. The main drawback is that, okay, it started quite early from now. It's only after, let's say, more or less the beginning of this century. So, as an example, let's start with use of models. I present here very briefly the MGB rain discharge model that we use in our group, but I know many people use other models such as the SWAT model and so on. More or less, they are working the same. All of these, even if you don't see it, okay, you use satellite data. In French, we have a very famous character who is Mr. Jourdain, who is talking prose without knowing it. Here it's the same. When you use this kind of model, you are using satellite data, even if you don't know that. In particular for the DEM, all these models need DEM. The DEMs were either from the shuttle or from satellite measurements. And the drainage networks also are extracted from these DEMs. All these models use map of the land use, soil coverage, and so on. Most of this information comes from satellite measurements. And of course, when you have to compute the vertical fluxes, precipitation and evaporation, in particular the precipitation, you have, as I will show, you have very good precipitation data that are available from satellites. So all these models use satellite. And once you have incorporated all this information in your model, you run your model, of course, you have to check the quality of your model. For example, with this model that we run all over the Congo Basin, we can see that we have quite a good natural cliff coefficient at the output of the basin that we consider when we compare with the gauge in not the gauge, the discharge series in Kinshasa. You see, this is the in red. You have our output, daily output, and the dotted line is for the gauge. Also, we can compare for the inundated surface, and this is what we have with our model. And you can see that it compares quite well with other attempts to map the inundated surface, and in particular, the very famous work by Peckel, who had problems because he mostly used visible images, and because of the coverage by the forest, he underestimates dramatically the inundated surface in the Congo Basin, in the central cuvette. Then, let's just again to try to validate this model. Let's check at the balance of the horizontal flow in the Cuvette Centrale. So, what we did is that we took all the discharge that is coming from the lateral flow that comes from the main drainage. The main drainage system, which is the upper part of the Congo river itself, with Walaba and Aruwimi rivers, the Ruki and Lulonga rivers, the Kasai River, the Bakete small rivers, Sanga and Ubangi. We took all these, the discharge in all these rivers, and we compare with what is going out at Kinshasa. So the red line is the discharge that we have at Kinshasa. You remember I showed you that the National Cliff comparison with the gauge in Kinshasa is 0.2, which is very good. Okay, and in blue you have the sum of all these lateral flows coming from the tributaries. The balance, the simple difference between these two, show this oscillating black curve here, okay, which is typical as what we can see is that you have some lag between the two curves. It's a bit between the two oscillating curves. And actually, if you make, just to see, if you apply a 15-day lag in the lateral inflow, the time series of lateral inflow, you see that your curve is almost flat, which means that the mean residence time of the water in this part of the basin is about 15 days. It's a mean value, okay, which of course should be improved by applying a specific lag for what comes from the Far East on the, for example, the Kasai, which is very close and so on, just to give order of magnitude. And this, so this balance has an average value of 1,800 cubic meters per second, which then is positive balance in the Cuvette Centrale, okay, which means that you have more water flowing out the Cuvette Centrale than getting in, and which is in very good agreement with the results presented by my preferred hydrologist colleague, Jean-Pierre Briquet, who I suggest you to see his poster, which is very interesting in how to share the water in the Cuvette Centrale from in situ measurement. So we can see that we have quite a good agreement between a model fed by and tuned by satellite data and what we can see with historical measurements in situ. And where, to be fully honest, I will show less good results, which is about the vertical fluxes. When we try to see at the evapotranspiration using this model, we have some equifinality limitations, which mean that, okay, we can have a good estimate of the lateral flows, but it's very difficult to see the share between what is infiltration and evapotranspiration. And as you can see, what we find in the central corridor is not that much different of what we have in the other rivers, and in particular, it's very similar to any results that you could find for a tropical basin. So we don't find any specificity of the Cuvette Centrale, but again, it may be a limitation of the model that has to be improved. And I could see that in some posters, for sure, we have some ways that we could improve the way the model is giving the evapotranspiration. Of course, another satellite data that is and that will become very, very important for the monitoring of the basins and, in particular, the Cuvette Centrale is satellite altimetry, because satellite altimetry will provide distributed values of the water level and then will enable, as I showed, that running models and having measurements upstream all the rivers that, in the upstream part of all the rivers that are both in the Cuvette Centrale. And I invite you to see the poster that we have by Joe Silva about this. And I don't know if it worked. So this is quite an old animation that I made, but using this data, we can monitor the water level in all the basin. You see the color code is from -1 for the lowest value to lowest anomaly. In red, the highest anomaly, and you can see the very well-known switch between the south and the north of the basin. All the small squares is where we have all the measurements daily. So, because not all of us trust in satellite altimetry, we decided to have a project in the Congo Basin itself to validate the satellite measurements, and in particular, the new measurements provided by the Copernicus European program. And as I will show you here, the results are really tremendous. It's important also when thinking about satellite data is that the evolution, the change in quality from what you can see from data 20 years ago, 30 years ago, on the data that we have now. So we installed a gauge on the Lobai River, which is the Sangha tributary northwest of... Ubangi tributary, of course, northwest of the basin. So this, you see the river is only 150 meters wide, okay? It's a narrow river, and this is just at the crossing with the Sentinel-3 satellite, and you can see the black dots are for the measurements made at the gauge, okay? And the red and green dots are the value given from the satellite. The color code is according to that if you take into account the slope of the river. But okay, and so from this, you see that the standard deviation is about 10 centimeters. If you take into account, in particular when you see at the curve, the decorrelation time of the signal, the water level in this river, okay, 10 centimeters is not so bad. It's really not so bad in terms of the amount of information that you have with respect to what you need in terms of hydrology. Anyway, if you take this altimetry data, you convert it into discharge. I will not go into details now, but we can do it. Okay, you have this black curve. Okay, all the Sentinel-3 measurements over more or less 2 years, and also we can convert them into water depths. That is, we can estimate a theoretical height of the water of the bottom of the river, and then make the difference with the water height into water depth. We got this red curve. And here the blue cross is the in situ measurements made by Jean-Pierre, you see, with the discharge value on the water depth. You see that, again, we are in very, very good agreement. Just to remind, that the applications of satellite altimetry, of modern satellite altimetry, will be that we can have the near real-time discharge throughout the basin for hundreds of points of measurements, even for very small rivers. Okay, this is an example, and we will post this very rapidly on our website in Toulouse. And also, another example of applications which is that you can combine it with DEM to have the altimetry profile of the rivers, even of the water line of your rivers, combining DEM with altimetry measurements. And again, once you have made the conversion of altimetry with discharge, you can also draw a profile of the river bottom, which is the red line, not very visible here, so that's why I made a zoom here. And we compare these depths with ADCP made by the CRUHM, excuse me, group with Paul Bates. Where is Paul? Okay, I think he will remember. And you can see, well, it's supposed to be, the drawing is not very good. This red line is supposed to be perpendicular, like this, from the longitudinal line, but you can see that you have a very good agreement with this mean theoretical depth of the river that compares very well with the in situ ADCP measurement. Now, another way to compare the satellite data is to compare them between themselves when you have no in situ measurements that you can compare with. This is an example of cross-validation of the water level with the rain data. You take all the rain data that you have over the Congo Basin, here it's over 7 years, okay? You can make, so you have some mapping in space and time. You take the same values from the water level, and you can make some empirical orthogonal decomposition of these two space and time data sets. This diagram shows the change in the mean value, okay, of these two data sets with time from 2003 to 2010. You can see that this mean value, okay, are very well correlated. They just have 6 to 8 months lag. Well, it's not very accurate, okay? But when you apply this lag, you have a correlation coefficient which is greater than 0.9, okay? For sure. So first, this shows that you have, of course, the water level is strongly correlated with precipitation, but that's not very new, okay? But it also shows that both data sets are very consistent. If one of these data sets was totally wrong, completely stupid, okay, we would not find such a good correlation. And if we go to the first mode, not the mean, which is the zero mode. If we go to the first mode of this decomposition, which means it is an oscillation within the basin, okay? Which, again, it's a very well-known signal from the north and south oscillation. You can see from this first mode, so the variation of this mode with time, okay, from 2003 to 2010, that the rain, TRMM, which is the black line, is very well correlated with water levels and with the DMI, which is an index of a climate index of the Indian Ocean. Okay, and if you just apply, oh no, it's here. Okay, if you just apply 2-3 months lag for the precipitation, and then 8 to 9 months for the water level, all these curves present very, very good correlations. So again, you can see that the processing that you can do with these data bear a lot of information, such as, for example, this climate information. Now, another data set which is very important because it enables to have information that cannot be collected in situ is the inundated surface. This is an example collected, well, it went too fast, sorry. And yes, an example made by Fabrice Papas, the GIMS product, that combines many radar observations, and that show you that we have the largest variation in inundated surface in the Cuvette Centrale. And when you combine this with the water level, you can have the storage, the water, the volume stored in the basin. I'm sorry, it goes too fast. It was much slower on my computer. And again, you can see that it's in the Cuvette Centrale that we have the largest volume stored in the basin. So you have the surface volume, as I showed, using the GRACE data, which was also an incredible satellite mission. You have the change in the water, the change of mass of water stored in the basin. I don't know if I can do it again. Yes, basin. And again, you can see the change between north and south. And this, with this GRACE data, you have the total mass of water. Of course, if you make the difference between the total mass of water and the surface water that I presented previously, you can see, you can split into what is you have on the surface and what you have infiltrated in the ground. Okay? Bon, this is an example of what we did. And bon, so I would love if someone could help us to understand what we find that the change in surface water storage is only 15% of the total water storage in the Congo Basin, when we find that it's more between 33-35 for other basins, such as the Amazon Basin and the Ganga-Brahmaputra Basin. I guess it's a question of the nature of the ground, but we are very open to discussion. Of course, this presently was at the global scale of the basin, but now you can split the same study into sub-basins, and in particular, all these sub-basins that surround the Cuvette Centrale. And so we can see that in the Cuvette Centrale, the black line, okay, which again, sorry, so it's the surface water storage, is much more important in the Cuvette Centrale than it is in proportion with the other sub-basins. Here we can see, we find again this question that we have the largest water storage in the Cuvette Centrale. So, as a conclusion, I'm sorry, I'm already late. And so I just wanted to say that the SAR data are becoming better and better. This is something, don't stay with old ideas about the satellite data. And they monitor new parameters such as the inundated surface, the total water mass, the slope of the water line, and so on. And they have a huge amount of information. And well, as I showed, relationship with climate indices, aid discharge, and so on. The big deal, I think, now is not to trust this data, is to think about how can we make them consistent with the hydrological information that was provided by the past archives. Okay, we had a huge amount of information from the past that had all the gauge data and so on, and the big deal is to make all these two data sets consistent. Okay? Well, and just to recall, that the rain discharge modeling fed and tuned by the remote sensing is now able to also reproduce very properly the horizontal fluxes and provide uncertainties. Okay, and this is consistent with the results are consistent with the studies based on in situ data. Okay, we just have with our model, but I guess other people maybe have not these limitations. We have equifinality problems with the vertical fluxes. So, just to conclude, I would like to recall you that the place to be during the poster session is to be in front of our posters. Okay, the one by Joësila or by Hadrien, we will tell you all what you wanted to know about satellite altimetry, but never dare to ask. Okay, and of course, Alice poster, who is here too, about the future SWOT mission. And this is just to recall you also our publications. And just to finish, I would like to say a big, big thank you to Doug for organizing this meeting and inviting us, and of course, to the true hydrologists, the best hydrologists I know, Alain and Jean-Pierre, for sharing their expertise with us. Thank you.
As you can notice, Mr. Stéphane already swallowed all the minutes given to them. But anyway...
No. Questions. Huh? Let's see if there's some questions. I think there might be some questions for Stéphane. We have time. It's okay.
Yes, questions? Yes?
And please use the microphone so that the interpreters can interpret.
Thanks for the very impressive and optimistic overview on what the satellite data can achieve. I was concerned about some of the initial comments that you made about the declining observing system. I'd agree that the observing system is declining worldwide. It's not just the Congo Basin. But the important thing is that for most parts of the world, where we understand the rainfall production well, we're moving from a position where that observing system was once very good. And in the case of the Congo Basin, we're moving from an observing system that was never good. So we don't have that grounding that we need, and I think that's an important point. The second issue is that we do have trouble with the rainfall satellite-derived data sets when we try and understand the meteorology of the region with sums to the climate. And that's because we're not spatially averaging it and temporally averaging it as much as hydrologists do. And there we're interested in individual mechanisms that produce storms and rain. And when you evaluate the satellite rainfall data sets with that purpose, there's huge differences between them that are problematic. And part of the problem is that the satellites see the cloud tops, but not the underneath of the clouds. And there's a lot of rainfall production that happens in mid-levels in the systems that the satellites can't see. So on a storm-by-storm basis, there's very big differences between the products. So the conclusion that the satellite products are good depends on the purpose that you're putting them to. Thank you.
So, okay. What I showed is that, again, the satellite products in terms of rainfall, okay? So which is the rainfall integrated rainfall over day, okay? Well, I'm not a rain expert, but I know that the people working with the new satellite, and in particular, for example, the Megatropic new satellite, the French-Indian new satellite, Megatropic, they have really very, very good results, even in the description of the structure of the cloud and the rain and so on. But I'm not an expert. I'm just talking in terms of the amount of water that they can provide. I would say like a gauge, okay, like a rain gauge. These results are really, and they are actually, the quality, as we can show, is far enough, is good enough, okay, to be used in rain discharge model, given in particular that you have a total coverage. You don't need to interpolate a few gauges throughout your basin in order to have a rain field, okay? Because you have measurements everywhere in your study area, which is also a very big point.
Hi, so I'm Guy Schumann. You may know me from the guy from YouTube. So first of all, very sorry I couldn't be here yesterday. And thank you very much, Stéphane. I don't know if I should translate my question. Probably not, because I see people with headsets. Okay. So I just want to very quickly, like your view on SWOT. I mean, you probably have a poster, but just very quickly, could you outline the view on SWOT for the Congo Basin? For the SWOT satellite mission, sorry.
Yes, SWOT satellite as, for the Congo Basin, as for any other basin on the world, okay, will provide full coverage of all the water bodies, okay, twice every 21 days, okay? The repeat time of the mission is 21 days, but because you have full coverage, just think about it, you have full coverage for the ascending, full coverage descending, so you have twice every 21 days, full coverage of all the water bodies that are more or less 100 meters pixel, okay? But we will average the measurements over 1 square kilometer in order to diminish the uncertainty. Maybe Doug could talk even more than myself about, because for everybody, Doug was the first PI for hydrology for this mission, and he probably is some kind of the father of this mission for hydrology. So please, Doug.
Well, it's a large group of people who are an international group who are doing the SWOT mission, and it's been several years since I was heavily involved. In fact, I switched in order to study the Congo. And it's obviously a lot of work to study the Congo, and so the SWOT mission is in wonderful hands right now with the team of people who've been moving it forward. But yes, it's just like Stéphane said, and the mission will be very valuable to us as yet another tool in our arsenal of tools that we can use.
Thank you.
And again, just, but very last word, all these measurements will be distributed for free. Everybody who wants to use them will be able to have these, either the height values, slope values, and attempt to convert them into discharge.
Merci, Monsieur Stéphane. C'est un sujet intéressant. Je crois que la discussion peut continuer pendant la session des posters et pendant lunchtime. Merci. À présent, nous allons inviter Monsieur Hyongki, excusez pour la prononciation. Il va nous présenter les sujets Determining Source of and Sink of Water in Congo Wetlands using multiple satellite datasets and Hillslope River Routing Model. Vous avez la parole, monsieur.
Good morning, everyone. It's my pleasure and honor to give presentation in this Congo Chapman conference. I'm going to talk about determining the source and sinks of the water in the Congo wetland using satellite data set and Hillslope river routing model. I would like to acknowledge my colleagues, Ting Yuan, who used to be my PhD student, now a postdoc at UCLA, and this presentation is mostly from her PhD dissertation work. Ed Bagley from Northeastern University, Han Chul from NASA Goddard Space Flight Center, and Dong-Hwan Kim, who is my PhD student. So here's the content. For those of you who are not really familiar with the satellite data set, let me give you some introductions about the remotely sensed data set that I've used here, which includes the water level changes from satellite radar altimetry, inundation extents from synthetic aperture radar, and the 2D water level changes from the interferometric SAR. And using those remote sensing data set, I don't know what happened.
I don't know either. That's weird.
Okay, all right. Let's see. All right. So using those remote sensing data set, I'm trying to test this research hypothesis.
It's not you. That's something else.
Okay, let me try again. So the first hypothesis is the water in the Cuvette Centrale is supplied. Okay. And the second hypothesis is whether the water empties from the Cuvette Centrale mostly by ET. So the first of all, satellite radar altimetry. So for those of you who are not really familiar with this satellite instrument, it transmits the radar pulse to the surface on the ground, and some of the signals reflected back from the surface to the satellite, so it measures the two-way travel time. And then we multiply, so it measures the two-way travel time multiplied by the speed of light, and we get the ranges from the satellite to the surface. And with the satellite altitude determined from GPS, we obtain the water surface heights. This is similar to what Stéphane has shown. So here's the ground tracks of the satellite altimetry tracks, and over the intersections between the altimetry and the water bodies, we're able to generate these kinds of water level change time series. And these are the examples from the altimetry called JSON2 and Sentinel-3. Next one is synthetic aperture radar. So it's basically a radar imaging technique using a microwave, which have this longer wavelength, ranging from 1 centimeter to 1 meter. And the advantage of using this synthetic aperture radar is that due to its long wavelength, it can penetrate through the cloud and the rain. Therefore, we can obtain the image of the surface of the Earth, even though over the places where it is covered by the clouds. Okay, now over the flooded forest, with its side-looking geometry, the signal is going to be reflected from the tree trunk, and then reflected again from the water surface. Some of the signals go back to the satellite. Therefore, we will have some brighter backscattering intensities over the flooded forest during the high water season. And you can see those variations, temporal variations of those backscattering intensities with respect to the amount of the water beneath the flooded forest. And using this, we can perform the classifications of the inundated extents using these radar images. So let me show you one case study that I did using this radar backscatter intensities with the mean vegetation continuous field, which is basically the tree densities, along with the satellite altimetry water level changes. Combining those three, I was able to obtain the water depth ranging from 0 to 1.4 meter for the Decembers of 2006, 7, and 8. And the reason why I'm showing this is because this is going to be used for the validations of the flood water storages that I'm going to present later. Okay, so about the interferometric SAR. So let's assume that the water level has changed between the SAR acquisition dates. And using this pair of SAR images, we can perform the interferometric analysis to obtain the water level changes beneath the flooded forest. So this is the, So this is the Congo main stem, and this is the Lulonga River, and this is Google Earth image. We can see from the spaces all these green features because of the forest. However, the SAR can provide us the water level changes beneath this flooded forest. So it gives us information on what is going on under those dense tree forest. Okay, so this is what I'm trying to do. So using INSAR and altimetry, I will first try to estimate the floodplain water storages. And then using the upland runoff from the HRR model developed by Ed Begley at Northeastern University, along with the precipitation, well, questionable precipitation data set, I would say, and with the ET. And through the water balance, I would try to estimate the river floodplain water exchanges. Now we have all the source and the sink terms, and by combining this together, we can try to interpret what is going to be the dominant source and the sink terms, and perform the hypothesis testing. The next one is that, again, using this inside altimetry in some way, we try to obtain the floodplain barrier topography, and then along with the river level changes in the, from altimetry, and comparing these two, we will also try to attempt testing the hypothesis. Okay, so first of all, this is our study area. So this is the Congo main stem, and these are the MVC altimetry tracks, and this red box shows the coverage of the SAR data that we have used. So there are actually 5 steps to obtain the floodplain water storages. So let me briefly go over these steps, and actually Ting Yuan, my student, my former student, has a poster. So for technical details, please ask questions to her. But let me briefly introduce what we have done. So here is the mosaic of the multiple interferograms generated using 2 SAR images obtained, one in low water season and the other in the high water season. And these are just the zoom view of this mosaic interferogram to show you how dense, dense fringes we are able to obtain throughout the floodplains of the Congo. Now, since interferometric SAR gives us only the relative, spatially relative water level changes, we need a vertical reference to convert relative to absolute water level changes. So in this case, we use the altimetry measurements to convert, to obtain the offset, and then convert this relative water level changes to absolute water level changes. And this is the result that we obtained. Now here, I said that this is water depth. The reason is because we have used the low water season SAR images as a master or slave images. So, and during the low water season, from our inundated extent maps is basically essentially dried. So we assume that this absolute water level changes is close to the water depth. So this is the water depth map that we obtained throughout the Congo area. And the next one is using this, the geomorphology of the floodplain geomorphology, and using these equations, assuming that T1 is from the high water level season, and once the water level has decreased by delta H, this is the equations that we try to use to derive the relationship between the water depth and the absolute water storages in those individual 8 study areas that we have identified. So these curves represents the relationship between the maximum water depth and the absolute water storages for each floodplain study areas that we have identified. The next step is now to using, again, the satellite altimetry. We're trying to generate the time series of the maximum water depth using altimetry data set. Well, this is the original altimetry time series. For each study area, we have like 2 virtual stations. Region A, this is for the region A, and region B. And this blue and red represents the water level changes from different virtual stations over the floodplains. And then we're trying to convert that into time series of the maximum water depth using this correction factor obtained from the water depth map that I showed in the previous slide. So this is now the time series of the maximum water depth derived from altimetry and the water depth map together over those 2 study region. And we have actually repeated this to all of the 8 study regions. Now, once we have this maximum water depth and we had this depth and volume relationships. So we are plugging this into the DV, depth and volume relationship, to obtain now the time series of the absolute floodplain volumes. So this is, again, for study region A, B, C, D, and so on. And then this is the time series of now the absolute floodplain water volumes from 2 different virtual stations. So the beauty of having 2 virtual stations in one study region is that now we have much denser temporal coverages. So as you can see, we have some peaks during the high water season around December of all the years. And the cyan circles represents the volume estimated from the water depth map that I have previously shown you using the sub-backscatter intensities. So comparing those water depth from my previous wool paper and from this study, it more or less agreed very well, validating the absolute water volume estimates from this study. And this is the time series of the absolute water volumes for the other study areas. Okay, now using that, absolute water volumes of the floodplains, now using this mass balance analysis, now delta S becomes known to us now. Now precipitation, we have used the trim data set, ET. We have used the Penman-Monteith equations with the MODIS data. This upland runoff provided from the HRR model. And now this is the unknown, and we can solve for this river floodplain water exchange because all the other terms have becomes known now. So here is the time series of those individual source terms and the sink terms over individual floodplain areas. So the positive flux represents the source terms, the negative flux represents the sink terms. So if you look at these for region A, the runoff is yellow and the precipitation is blue. So as you can see, and this red is the river exchange. So at some years, during the high water season, we see some positive river exchanges. That means that river exchanges has some role, however, very small compared to the contributions from the upland runoff and the precipitation. And also, if you look at the sink terms, so there are 2 sink terms, which is a river exchange and also ET. So as you can see, well, the ET seems to be larger than the river exchanges, but river exchanges is not negligible. It's actually also contributing significantly to the sink terms. And this is more or less the same interpretation, same results that we get for over the other regions. And this is the summary of those sources in the sinks. Now this is in percentages of the river floodplain exchange, precipitation runoff, river floodplain exchange in the ET for all of the study regions shown over here. And as you can see, source terms is mostly upland runoff is the most dominant, seems to be most dominant term, and the precipitation and the river contributions is relatively very small, and then for the sink terms, the river seems to be quite significant, but ET is also contributing a lot. Right, so for the hypothesis, so the first hypothesis, the water in the Cuvette Centrale is supplied mostly by rainfall. According to our mass balance analysis, it seems to be true. Now, the second hypothesis, the water empties from the Cuvette Centrale mostly by ET seems to be false because also the river floodplain exchange also plays a significant role in the sink. So it seems to be false. Okay, so the next result that I would like to show you is the floodplain barrier topography that we obtained from the INSAR and altimetry. So this is the simple equation that we use to derive the floodplain barrier topography. So here's the high water season water surface that we have generated from the altimetry observation and performing some interpolations. So this is the water surface, high water season, water surface elevation during the high water season. And now this was the water depth map that we have generated already from the previous study. So by subtracting these two, we are able to obtain this bare earth floodplain topography. Okay, so how do you know whether that's correct or not? So we try to do some comparison with the ISET elevations. So this x-axis is the ice-set-derived bare earth topography. This y-axis is the elevations from various DMs. So here, this red dots represents the floodplain bare earth topography obtained from INSAR altimetry. And this blue one is from SRTM. This, see, the black one is from BEST DM, and this green one is from the MERIT DM. And so, of course, this is the DM elevations extracted over the ice-set footprint locations, of course. And by doing the comparison, as you can see, our floodplain bare topography seems to agree very well with the ice-set-derived elevations. And it is well known that SRTM has higher bias because of the canopy heights. BEST DM, MERIT DM, trying to remove those canopy heights. And it also agrees reasonably well with the ice-set-derived elevations. And this is the histogram of the error, or the difference from the ice-set elevations. Okay. So as you can see, this red one is again from our floodplain bare earth topography, so it's very well centered at 0. And the SRTM DM, this is the MERIT DM, and this is the BEST DM. So as you can see, our floodplain bare earth topography seems to be, makes sense. Okay, so this is another comparison among different DMs along the profile of the ice set. So we had one profile of the ice set. So these are the floodplains, and there's a river in between. So please ignore these straight lines in the river. But if we again compare the profiles of the height from SRTM DM, which is blue, MERIT DM green, this BEST DM from black, and this cyan color represents the ice set elevations. This red one represents our floodplain bare earth topography. So to show that our bare earth topography is a reasonable estimate. Okay, now using this, what we are trying to do is now over these virtual stations, over the rivers, so we are able to generate these river level changes over those locations of the virtual stations. And then across, so we're trying to extract the floodplain bare topography along these cross sections perpendicular to the river flow directions. And then we're trying to compare those two. So over, for example, over these virtual stations, this blue line represents the river level changes from altimetry, and this shaded area represents the floodplain topography range across those the profiles that we selected perpendicular to the river flow directions. So by comparing these river level changes and the range of the floodplain bare topography, we can have an idea whether the river can flow uphill to the floodplain area or not. So by looking at these two cases, it is obvious that only at some, some years which has this highly peak water levels, it may be able to, the water level has risen high enough to flow into the floodplain area. But during the other years, it cannot. But however, we have only 7 virtual stations in this case. And for example, in this case, it seems like the floodplain and the river may interact intensively. So here is the time series for other locations of the virtual stations. As you can see, over some of the years, some of the high peak years, the river may contribute to the waters in the floodplains. And in this case, it seems like, again, the floodplain and the river may interact intensively. However, we have to be careful about also the accuracy of the floodplain bare DM that we derived. The accuracy was about ½ meter, so we have to also think about that, consider that when you interpret this correctly. Okay, so the first hypothesis, the water in the Cuvette Centrale is supplied mostly by rainfall, seems to be true. Okay, again, because of the comparisons between the river levels and the floodplain bare topography, it seems to be true. However, at some places, extensive river floodplain exchanges seem to happen as well. Okay, now here's the conclusions to wrap up. So the upland runoff and rainfall contribute more than 85% of the total water inflow, while the river exchange supplies less than 15% of the total water inflow. And this irreversible change contribute more than 59% to the total outflow, while ET contributes less than 41% of the total outflow. Now, floodplain topography generally exhibit higher elevations than the river levels, but exceptions also exist at some places. So this is all. Thank you for your attention.
Nous remercions M. Hyongki pour sa présentation et surtout pour donner déjà lancer les possibilités sur les hypothèses que nous allons vérifier lors de notre discussion. Questions? Est-ce qu'il y a des questions? Questions?
Well, first off, thank you, Hyongki. But I will be really interested from our carbon discussion this afternoon, what they will think about the carbon dynamics and the evasion of carbon in the wetlands, particularly as these water flows are interacting or not interacting between the wetland and the river. I think that'll be a fascinating comparison to be made. This is a really fascinating presentation that Hyongki has given us, so thank you.
Merci. Merci pour cette présentation. Je ne suis pas du tout spécialiste de vos travaux. Moi, je suis hydrologue de terrain. Et donc, par contre, ce que je sais, c'est que dans cette zone de la Cuvette Centrale, qui est très très plate, vous l'avez remontré très très bien, il y a énormément d'échanges de rivière à rivière, de cours d'eau à cours d'eau. Il y a même des cours d'eau qui changent de direction en fonction de la saison. Donc, comment cela peut être pris en compte dans votre analyse?
Try to, I'm not sure whether I understood your questions correctly, but I think you mentioned the water exchange, water directions changes.
There are some rivers, it's so flat area, you have some rivers, they flow in both directions, according to the water level or to the season period. So how you can take this one into account in your system?
Okay. Well, here what we have assumed is this the floodplain morphology like this, and using our water mass balance analysis, actually we haven't considered the slopes or the water flow directions changes in the flat regions, and actually our study area here is perhaps the area that you mentioned, perhaps maybe more downstream of this main stem here, but the study area that we have done here is actually surrounded by the higher upland topography. So also, well, I haven't included the results in this slide, but we have also performed some water flow direction study from the floodplain to the river using INSAR again, because from these water level changes, we can interpret where the water flow directions based on these fringes. So the water should flow from these directions to that directions based on the directions of the fringe, and that also made sense based on the elevations of the surrounding topography. So what we have discovered is that the water empties, the water in the floodplain empties into the river from our interpretation, and which was also in agreement with our conclusions from the study that I presented. I hope that answered your question correctly.
Yeah, very nice presentation, and thank you for making the link to the hypotheses as well. Just very quickly, probably more a statement rather than a question. Here again, the SWOT mission I think would be particularly useful because it simultaneously measures, or will measure hopefully, the extent and the water level change, so you may be able to get a better handle on on the actual volume storage, because it's, in your case, I think there may be, there could be some changes in time, you know, when you take the inundated area and the INSAR measurements to do the volume. I don't know, you've been probably very careful with the high and low season, but here's what would particularly be helpful, so hopefully you can contribute to this as well.
Yeah,
Thank you.
So the thought on SWAT over Congo is that SWAT is using Ka band. Now, Congo, not only Congo, but like, you know, tropical forest, which is heavily covered by the tree canopies. So I'm not sure whether perhaps someone can, you know, answer these questions. But my question is whether the SWAT is going to, you know, able to contribute to the Congo hydrology. Of course, it will provide the river elevation changes over the open rivers, but perhaps it may be very difficult to obtain such water level changes over the, you know, vegetated floodplains.
Thank you very much, Professor Lee, for your presentation. So I have a simple question. So it seems like from the methodology of the radar used here, like sometimes you depend like the microwave like to reflect by the tree and then to measure the water level. So I just wonder like if there's any like deforestation happens along the river, so would that affect the measurement of the water level? Thank you.
Yes, so yeah, so because SAR is a side-looking, you know, instrument. So if it's just like open water, let's say, then the signal transmitted from the satellite is going to reflect away from the satellite if there is no tree. If it's just perfectly open water, such as over the river, because open water is going to play a role such as just a mirror. So the radar signal reflected on the water surface is going to reflect it to the other directions of the satellite, and little energy is going to receive from the satellite. So in that case, we cannot, well, we can use SAR backscatter amplitudes to delineate the open water bodies. However, we cannot use this interferometric SAR technique to obtain the water level changes, because we need this vertical structure for this radar signal to be reflected back to the satellite. So if there's like a deforestation, that means that if we don't have any trees, then we cannot apply this interferometric SAR technique to obtain the water level changes. But we can still use the backscatter intensities to delineate the extent of the water body.
Thank you.
Ellen.
Merci beaucoup, Lee, pour cette présentation très intéressante. Alors, vous avez dit que les échanges dans la cuvette, il y avait énormément de pluie, peu d'évapotranspiration. En fait, ce que je voulais savoir, c'est si, c'est pas vraiment une question que je vais vous donner, c'est plutôt un commentaire, une information. C'est que dans la cuvette centrale, il y a énormément d'échanges verticaux et je ne sais pas dans quelle mesure les satellites peuvent enregistrer cela. Je m'explique, il y a énormément de pluie convective, c'est-à-dire il pleut, ça s'évapore tout de suite après et cette évaporation va réengendrer une pluie. Donc on a un cycle perpétuel vertical d'échange pluie, évapotranspiration, pluie, évapotranspiration. Alors je ne sais pas dans quelle mesure les satellites peuvent quantifier ce bilan hydrique vertical.
Well, I'm not really the expert of precipitation or evapotranspiration, but to answer, as far as I know, I don't think there's any satellite measurements to provide those, quantity, because the satellite rainfall is just measuring the rainfall, itself, and the ET that we use in this analysis is using the temperature and the leaf area index and albedo obtained from the MODIS data set. So I think my short answer is no, but if Ed or anyone else can, answer that in more detail.
Well, I'd say for the ET, we're definitely not capturing that. We're just doing the radiation budget to drive the ET process with the Penman equation. So that idea of convective rain and then evaporating immediately, or transpiration, quickly, I guess more of an evaporation, that's not sort of the mechanisms that are getting modeled for the ET. And so the satellites, if they see it, they're just seeing the rainfall, to my knowledge, and not capturing that sort of net effect of no rain with the quick evaporation. I don't think it's being captured.
Alors, il y a peut-être l'apport des isotopes qui peut renforcer la connaissance. L'étude des isotopes de l'oxygène et de l'hydrogène peut peut-être contribuer à quantifier l'évaporation dans la quantité des pluies. Alors, il y a peut-être des géochimistes ici qui pourraient donner plus de compléments d'information. D'où l'utilité, effectivement, comme l'a dit Stéphane, comme vous le dites vous aussi, de croiser tous nos regards, l'hydrogéochimie, la télédétection, la modélisation et effectivement les données d'hydrologie au sol pour arriver à comprendre le fonctionnement de cet hydrosystème vraiment complexe et passionnant. Merci beaucoup.
C'était la dernière question. Nous allons terminer par là, malheureusement. Nous remercions M. Hyongki pour sa présentation. Nous allons passer au troisième présentateur, qui est M. Paul Bett, avec sa présentation « Gaining Insights into the Surface Water Dynamics of Cuvette Centrale using Hydrodynamic Modeling ».
Okay, thank you, Jose.
Just a second, Paul, before you start. I will say that the technician is monitoring the computer and the screen from up there, and hopefully it'll be okay while you, and if not...
If not, it's not. It'll be fine. Thank you very much. Hopefully this talk, I think, will complement very well those by Stéphane and Hyongki, and particularly Hyongki's talk, because I'm going to try and address the same hypotheses using a different set of techniques, and we'll see towards the end of the presentation whether I come to similar or different conclusions. So what we're going to do in this presentation is explain our research using two-dimensional hydrodynamic models to simulate the surface water flows in the Cuvette Centrale. And this work is based on the modeling of Fikra O'Loughlin. And so really these are Fikra's results that I'll be presenting here. But I'd also like to thank my co-authors Jeff Neal and Ed Begley, Guy Schumann, and also the Crum project team who are here as well. So, study area, we've looked at this a number of times. I don't need to go through too much or tell you about the region. But the point I'd like to make is we know relatively little about the surface water behavior within the Congo Basin. It's one of the largest percentage of the world's wetlands and limited in situ measurements. But we do have tools that we can use to build numerical models of this reach and the surface water flows. We have rainfall runoff models, such as the one that Ariane develops and the one that Ed develops, that can provide the boundary conditions for hydrodynamic models. And as Hyongki has pointed out, we have digital elevation datasets, which are the other key input to these codes. So we've built, for this region, one of the world's largest two-dimensional hydrodynamic models, covering the area shown in this slide in red. It covers 1.5 million square kilometers and contains almost 13,000 line kilometers of rivers. And we're going to use this model to try and answer our two hypotheses. And the way we're going to do that is relatively simple. We're going to simulate the surface water states using the model, and we're going to condition that model against available remote sensing data so we have some confidence it's doing the right things for the right reasons. And then we can switch off different model components in sequence and use that to test the above hypotheses. So it's a relatively simple research design. So the methodology, very simple. We have a numerical model which solves the shallow water equations which predict surface water flows in 2D, and that's our LISFLOOD FP model. We drive the model with input data, which primarily is the digital elevation model, some either gauged flows or flows from a rainfall runoff model, and friction parameters. We have river widths that we can get from satellite data, and our big unknown data set are the river depths, and we have a single model parameter, which is the surface friction. We can get at those unknown frictions and river depths using a calibration optimization technique and the ENVISAT satellite altimetry that Hyongki has described. So we can use ENVISAT measurements of water surface elevation and an calibration optimization procedure to estimate our unknown river depth and friction parameters. And we can use that system to provide estimates of surface water, and we can also drive it with evapotranspiration as well. So, in terms of input data, critically, the DEM is one of the most important things in hydrodynamic modeling, and Hyongki has talked a little bit about the differences between the SRTM dataset and some of the processed alternatives. Original SRTM, as Hyongki has explained, is corrupted by vegetation artifacts, and in a tropical forest area such as the Congo, that is extremely important to deal with. Fortunately, Fukuura and Dai Yamazaki in Japan have spent some time and considerable effort working out clever ways to clean up the DEM data and remove the vegetation artifacts. And we make use of other remote sensing data sets that estimate vegetation heights on a 1 kilometer grid. So we can take the original SRTM, we can take a remotely sensed data set of vegetation height, and a simple subtraction will give us a vegetation-corrected DEM. The one we're using here is Fukuura's best DEM, but equally we could use the merit system as well. And you can see, well, it's rather difficult to see in this image, I have to say, but the vegetation correction really improves the representation of the land surface in the Cuvette Centrale. And the other key data set that we require to drive this model are gauged flows in all the rivers. And we have 5 in-situ gauging stations that we can use. And together they account for 58% of the discharge that we measure at Kinshasa. So we're missing some flow, and we're missing some tributaries where we don't have gauges. So we need to pull in those data from somewhere else. And in this case, we use Ed Begley's HRR rainfall runoff model. So at the locations with the black dots, we take discharge from the HRR model, those 12 locations, and that accounts for the other missing discharge, or most of it at least. So about 5% is actually missing from these observations. Nevertheless, given that we can only measure discharge in rivers to typically 5 to 10%, that's within measurement error. And then lastly, calibration. Here we use ENVISAT measurements of water surface elevation, so this is a satellite altimeter. We have observations at all the white dots along the main stem and some of the tributaries. So 33 locations, and we obtain those from ESA's River and Lakes database and also from the team at Lagos. The bathymetry and the friction are calibrated for each subreach between the ENVISAT locations. So we don't have a single value for friction. We have a single value for friction, but bathymetry which varies in space. And we have 33 piecewise reaches for the bathymetry. Now, we have 2 unknowns and a whole bunch of different dynamical observations of the model states. And this gives us an unconstrained nonlinear minimization problem. But computational tools do exist to solve those things, and we use a routine simply within the MATLAB toolbox. We need, however, to do a lot of simulations with the model to back out unique parameters for all of those bathymetry parameters for all those reaches and the friction. And we take about 6,000 simulations to do that, And with the model that we've built, that takes about 6 weeks of compute time on a machine with 48 cores. So not a trivial computational undertaking, but not impossible either. And here's the research design. We have 4 simulations where we have a control simulation, number 1, and then 3 others where we switch different model components off. So just to go through the control simulation, the DEM comes from the vegetation-corrected SRTM of O'Loughlin and al. Discharge, as I've said, comes from gauge data and the HRR model. The river widths come from Landsat average values per model grid cell, and that also comes from another publication by Firker O'Loughlin. River depths are calibrated per reach. Friction is calibrated. Actually, this is a mistake. There is a single friction parameter. Evaporation comes from the CRU average monthly values. We're not including terra firma runoff in this simulation. The model resolution is 4 kilometers. It's, I would say, a medium resolution, and that's because of the computational cost of the optimization procedure that we use. It's worth pointing out that these numerical models, the computational cost is strongly dependent on the grid size. If you halve the grid size, so if we went to a 2-kilometer model, the cost of running the simulations would go up by an order of magnitude. So instead of the optimization taking 6 weeks, it would take 60 weeks. If we went to a 1-kilometer model, it would take 600 weeks in order to run the optimization. So it's a very strong dependency on the grid size. And by 4 kilometers, we make the problem computationally tractable. And then our 3 other simulations. Simulation number 2, we turn the evaporation off to see what effect that has. Simulation 3, we actually stop the channel interacting with the floodplain. So we can just set the floodplain elevations to, say, 5 kilometers, and there's going to be no interaction between the channel and the floodplain there. And in the 4th simulation, along the Congo, we have a number of places where the river width really constricts. And Firker has shown that those have a strong hydrodynamic control. We can play with the model and take the effect of those constrictions out so that they're not producing a hydrodynamic control on the wave propagation. So these are our 4 simulations. First of all, the question you will want to know the answer to is, does the model work? Does it produce simulations which are sensible? Well, we can have a look at our control validation and look at the differences in the modeled water surface heights and that observed with the MVSAT data. So here you see for the 33 virtual gauges, this is the root mean square error. So overall, we've got a root mean square error between the model water surface elevations and those that are observed with the MVSAT satellite of 0.48 meters with a bias of minus 0.19. Now, the SRTM digital elevation model is, in its original state, is integer values. It is only provided, quantized to the nearest meter. So this RMSE is actually less than the precision of the SRTM DEM in its raw state. So this is about as good as a numerical model is going to be able to do with such DEM data. So here's some examples of hydrographs at places where we do well and places where we do badly. So at location number 5, the model is doing a pretty good job of predicting the water surface elevation at that point. And 23, this is our absolute worst case scenario. The RMSE is way over 2.5 meters, and you can see that there's a significant bias here. Importantly, where we do have these big RMSEs, most of that RMSE is coming from bias. There might be an error with the DEM locally in that position. It might be a problem with the altimetry measurement. We don't have a way of knowing, but it's more useful that it's a bias than it's actually a random error. And here are some, we do slightly less well on the tributaries. The RMSE goes up to 1.051. This is because they're narrow rivers. And you can see a couple of examples of our prediction skill of water level along the tributary rivers. And what this is telling us is that in a distributed sense over the entire river network we simulate in this model, we're getting the water surface dynamics pretty much correct. We have some RMSE, but it's explainable within the error of the DEM, and we're getting the right timing of water elevation changes at all of these points. Looking at how that model simulates the flows at Kinshasa, so that this is the observed discharge at Kinshasa with a 10% uncertainty bound, and this is the model discharge that's coming out of the model. So we're getting the wave routing reasonably well approximated at Kinshasa. We're mostly within the uncertainty bound of the discharge, and we're doing a reasonably good job with a Nash-Sutcliffe efficiency of about 0.4. And remember, we've got a 5% volume error in the model. Let's try another couple of bits of validation. This is model simulations of inundation extent compared to the data set of Catherine Pridgent and Fabrice Papa. This is the GM's data set. So GM's has a bit more of a dynamic range than the model does in terms of inundated area. And you can see the impact of the research design simulations that we have. So in red, we have the control simulations. If we turn the evaporation off, which is simulation number 2, we of course get a more inundated area. If we smooth the widths, the constrictions, we get water flowing out of the model much more easily, and less water is retained in the model, and the transit times are quicker. So the model's behaving according to the switches we're making in a physically realistic way. So Catherine and her team have the modeled inundation extents between 20,000 and 40,000 kilometers squared. We model on a narrower range between 25 and 35,000 kilometers squared. And Hyongki, in a paper in 2014 for a similar area, gets a dynamic range of inundation extent of about the same order. So these different data sets are telling us that rather similar things about the inundation extent, and it suggests the model's doing approximately the right thing. So here are some inundation extents that we get from these models. This is the Pridgent et al. Data set, and it's provided at 0.25 degree resolution. The model's actually working at 4-kilometer resolution. The Pridgent data set is the fractional flooded area at 1/4 degree. The model's working at 4 kilometers, but we can turn this into a fractional flooded area at 1/4 degree resolution to produce a like-for-like comparison with the Pridgent data. And you can see that there's a reasonable correspondence between those two data sets. They're not identical, but they're coherent. And lastly, we can use the GRACE data set, which is the measure of water volume, to look at whether we have the right water volumes in the model. So here are our 3 simulations. This is the floodplain water volume, so we have the control, the no evaporation simulation, and the smoothed widths. I'm not showing the no floodplain simulation in any of these because we're looking at floodplain volumes. So the average annual total storage change within the model is about 65 cubic kilometers. The average annual floodplain storage change is about 31 cubic kilometers, and that compares to some of Hyongki's estimates reasonably well. So we're getting the right amount of water moving to and from the channels and the floodplains. So interrogating that research design and that model setup, we can draw some conclusions about the behavior of surface water dynamics in the Congo Basin. So the model's suggesting that river water is exchanged with the floodplain. So this is consistent with the information that Hyongki's just told us about, but using a different set of tools and techniques to arrive at a similar conclusion. So I'd suggest that if 2 different science studies using different methods are telling you the same thing, we can have greater confidence in the conclusion as opposed to either study alone. So there's much lower exchange volume here in the Congo than in the Amazon. According to some data by Doug, it's 4 or 5 times as much in the Amazon as in the Congo. But the model suggests that the interactions between the floodplains and the channels are extensive. They occur over about 2,100 kilometers of river within the model. So there's many areas of river channel within the Cuvette Centrale where water is being exchanged with the floodplain. And again, this is consistent with the information that the findings of Hyongki's team using a different set of methods. We find out as well from the model that the bimodal annual hydrograph is a hydrological, not a hydrodynamic feature in the basin. Things that we're doing to the hydrodynamic model and within the hydrodynamic model itself, so the evaporation, the floodplain interactions, and the river widths, they have some effect on the wave propagation, but really they don't change the overall bimodal pattern. They change the timing and the peak to only a modest extent. So largely the bimodal feature is hydrologically controlled. The evaporation changes the speed of floodplain wetting and drying, but it doesn't really change the overall maximum and minimum inundation extents. And looking at our calibrated river depths, so we've used the model to back out what we think the river depths should be in order to recreate the surface water elevation dynamics that we observe in ENVISAT data. So the model is giving us an estimate of what the river depth along the Congo channels should be. And they're approximately 6.5 meters on average, with 2 or 3 meters of annual stage variation. And we can't get at bathymetry really in any other way apart from going out and conducting a very extensive bathymetry survey. The caveat here is that all of these results come from a model that's conditioned against observations rather than from observations themselves. So you have to take into account the uncertainties in the model and its data in interpreting these conclusions. But some of these points are so strong that I think we can be relatively confident in drawing them. So let's go back to finish off and look at the hypotheses, same as Hyongki. Now I think the key word here is mostly. So can we say anything about whether the Cuvette Centrale is mostly supplied by rainfall and empties mostly by evapotranspiration? Well, I think the experiments I've shown only partially test this because we haven't, I think Hyongki's experiments were much more comprehensive in terms of a test of these hypotheses. I think what we have been able to show is that the channel floodplain interactions are an important part of this story. So that's very consistent with Hyongki's conclusions as well. So I think we can be relatively confident in that outcome from these modeling. So it may be the case that the water is supplied mostly by rainfall and empties mostly by ET, but there is a non-negligible, a significant but contribution from channel floodplain interactions and hydrodynamics. So, sure, you should go and see the posters from Stéphane's team, but you could also go and see the posters from our team as well. And you'll be equally enthralled by these. And this will tell you some of the later research that we've done to try and unpick in more detail the channel floodplain interactions. So Lawrence Hawker has been running a statistical connectivity analysis over the floodplain DEM, and then using DEM stochastic simulation to look at the interactions between the channels and the floodplains. Ferko Lachlan has been looking at old Russian maps of the floodplain, which show floodplain channels on them. And he's been rerunning the model with those channels inserted to see if they change the inundation extents and volumes we predict on the floodplain. And lastly, Jeff Neal has been using not a hindcast simulation where we simulate many years of real dynamics, but he's produced a flood risk analysis for the Congo. Now, the advantage of that is that we don't need to do the optimization or run many years of data. We can just simulate the 1 in 100-year flow everywhere over the basin. Because of that, we can make that model much finer resolution. In fact, the model that Jeff has run over the Congo is 100-meter resolution. So if you go and look at Jeff's poster, there's a fantastic inundation map simulated by a numerical hydrodynamic model at 100-meter resolution. And I encourage you to go and look at it because it's an absolutely awesome looking result. That's it. only leaves me to say thank you very much for your attention and inviting me to speak.
Merci pour cette présentation. Nous allons passer directement à la séance des questions-réponses. Question. Question. Yes.
More a comment than a question about the altimetry data that you use, Untitled data.
Stéphane, come on now. You have to get up and put your computer away and come to the microphone, or you'll have to do your own interpretation for us. While Stéphane comes to the microphone, I will say this. Judy has arranged we will take our picture outside on the steps, and I'll talk more about that in a second.
Just because the results you showed with respect to the Envisat data, is that I could see that you took the data from different sources.
Yep.
You should have taken only from Lagos, but whatever. But the point is that all these data are quite large biases. Okay. So I don't know, maybe you remove the mean values or something to remove these biases, but you may have inconsistencies between the Envisat series that you took, for example, from River and Lake and our series, just because they were processed different way, and then you have some biases that may be part of the biases that you see. And well, just to say that if you want, we can talk about it later.
Yeah, thank you, Stéphane. I think that's a very good point. And I'm conscious as well that there are many other sources of altimetry data that we haven't thrown into this analysis. We could be including the Sentinel-3A data, for example, or some of the other altimetric satellites that have gone up. So I think there's more work to do here. I think Hyongki also shows some very nice interferometric SAR data and SAR inundation extent imagery, which is of higher resolution than the Catherine Pridgeon data set. And again, I think as we move forward, we'd like to improve a number of aspects of both the model and its input data. Any other questions? Another question? Coffee is calling.
Nous remercions M. Paul Batz pour sa présentation. Ainsi, nous avons terminé notre session de présentation. Nous allons nous retrouver à l'exposition des posters pour essayer un peu de visiter, discuter. Et nous devons avoir à l'esprit des hypothèses que nous avons posées et essayer de trouver des réponses à ces hypothèses. Merci.
So, a couple of things. Let's walk from here, go to the round tables where the lunch is, and then there's a door. We will walk right out onto the steps. The steps that are on the west side of the building. It's in the shade right now. We'll take our picture very quickly. Everyone who wants to be in the picture, you go out there and get your picture. It'll be done as a group very quickly. Then we come back in and cool off. A second thing I want you to talk about during the posters. Would you be more comfortable having one discussion group in here instead of two separate groups? Let me know what you think while we're wandering around, okay? So let's go get our picture.
Nous descendons les escaliers pour prendre une photo de famille.